All right, friends, it is Thursday. We are going to get started with our bell work. You should have your binder out in front of you. I'm going to read the question for you first, and then you'll have 3 minutes to complete it. It says, pick the terms that best complete the sentences. Blank is the ability to cause change. Blank is energy of motion, while blank is energy based off of the position or configuration of an object. Which terms best complete the paragraph? A, energy, kinetic energy, potential energy. B, potential energy, kinetic energy, potential energy. C, energy, kinetic energy, chemical energy. D, kinetic energy, potential energy, chemical energy. Right? You have 3 minutes. Pause the video. Right, let's review the question. Right, so first of all, the first one says blank is the ability to cause change. Right, anything that's causing change is going to be energy. Right, it has the ability to do something. So looking at our answer choices, we're down to A and C. You could cross off B and D. Right, it's not potential, it's not kinetic. Blank is energy of motion. Right, we know that kinetic energy is energy of motion. So kinetic energy, we're both on the right track. We still have A and C. And last one, while blank is energy based off of the position or configuration of an object, that's going to be potential energy, right? The position has nothing to do with chemical energy, right? That's how something is stored. So A is our correct answer, right? You should have justified this question as well.
It's incredible to think about all the physics involved in executing the pole vault. Much of it boils down to the basic principles of kinetic and potential energy. Okay, let's rewind and take a look at the athlete at the very beginning of her jump in terms of energy. Even before she begins running, while she is standing still and visualizing her jump, the athlete needs enough chemical potential energy from food to supply her body with the energy she needs to run and gain enough speed to make the jump. This chemical energy is then transformed into kinetic energy by her muscles as she begins to sprint towards the bar. Once she plants her pole and it begins to bend, her kinetic energy is transformed into elastic potential energy. Elastic potential energy is energy stored as a result of applying a force to deform an elastic object. In this scenario, the pole bends, or deforms, and acts like a loaded spring. The energy is stored until the object springs back to its original shape. The pole has the greatest elastic potential energy when it is the most bent. As the pole vaulter begins to lift up, the pole unwinds and the elastic potential energy is transformed into kinetic energy and gravitational potential energy. The vaulter gains vertical speed and height as she moves up off the ground. When the athlete is at the top of the bar and the pole is at its straightest, the pole now has the least amount of elastic potential energy, and the vaulter has the greatest amount of gravitational potential energy. As she falls back down to the ground, her gravitational potential energy is transformed back into kinetic energy. Once she lands, her kinetic and gravitational potential energy becomes zero. Considering what an incredible athletic feat pole vaulting is, it's also surprising how it can be explained using simple principles of kinetic and potential energy.
All right, this is the next thing we're going to be doing today, right? It is a foldable, right? And it says understanding potential energy. It looks like this. It has what's called a pendulum on it, right? This paper needs to be passed out right now. Students should also have their piece of scratch paper from yesterday, from the days before in their binder that looks like this that had the other foldable on it. Right, we're going to be using this today and gluing this foldable to the back of it. So go ahead and get this paper out as well. you should have these two things out in front of you. You should also have a glue stick. If you don't have one, make sure you are borrowing one from a friend or finding one on a desk. So pause and make sure we have everything we need. I'm going to put this paper off to the side, and we are going to get started with the foldable. Right, so again, this foldable is kind of funky. We're going to be writing things all over it, so make sure you're following along with me, and you can pause the video if we need to. I'm going to turn, and we're going to be focusing down here in this little blob first. Right, so in this little box, we're going to write energy. Let me zoom in. Can never be destroyed. That is something we talked about on our notes. Remember, I called that the law of conservation of energy. It can never be destroyed. Very important. Right, now I'm going to slide over to the pendulum at the top. Looking at these arrows, right, this is what's called a pendulum, right? It works kind of like this. It's fixed in one point at the top, right? And you would pull it back and drop it, and it's going to swing back and forth, right? So up here and over there, those are going to be the highest points of where it's going to go, right? So we're talking about gravitational potential energy again, right? Looking at these arrows, because this is the highest, that tells me that the GPE is going to be the highest point because it's the highest point in this system. Right? The KE is going to be the lowest, right? Because as you drop this pendulum, it swings back and it swings back, right? At the very top, it stops before it changes direction, right? So that's why the kinetic energy is the lowest, because it's stopped right here at the top, right? Over here, however, right, as you drop it, you see the arrows going this way, right? Your GPE starts to go down, and your KE starts to go up, right? Because it's at the highest, it's starting to go closer to the ground, and it starts to move faster as it goes, right? So that is the transformation we see there, right? Now we're going to flip it to the other side. It looks like this, right? I am going to warn you, this is going to be a lot of writing, but we got this. You can do it. Right, we're going to stop in this top corner right here. This is also a part of the pendulum that we saw on the other side, right? So we're going to put PE. Remember, this is GPE, sorry. Right, GPE is the highest, KE is the lowest. That's going to be at the very top, right? Right, now let's move to work right here. Let's define what work means, right? Again, it's a lot of writing, but you can do it, right? Work is a change in temperature, speed, position, pressure, or form of matter as a direct result of energy in a system. Right? Work basically means a change happening, right? A change happening as a result of energy, right? That's the shortened version. Go ahead and pause and make sure everybody gets that. Now I'm going to slide down to joule. That's how this is pronounced. Joule, not joule as in like a diamond, right? Joule as in a unit of measurement, right? What I'm going to do for this is I'm going to pause, I'm going to write this, and I'm going to come back. So you're going to pause the video in a second. All right, I'm back. Right, go ahead and pause the video and write this. It says a joule is the unit used to measure energy, the amount of energy that's needed for a change within a system. Right, so just like we talked about newtons in our last unit about forces, this is going to be joules. Right, so for example, a system could have 100 joules of energy within it. Right, joule is just the unit of measurement, just like inches and feet measure length. Right, now we're going to slide over to variable. Right, I'm going to go ahead and write this whole side and come back in just a second for us to talk about it. All right, I am back. What we're going to do is I'm going to read through each section. After I read the section, you can pause and make sure you have the rest of it filled in. All right, so starting with variable at the top. A variable is something measurable that can change. Right? We have dependent and independent variables, right? That is something we talk about when we're doing labs, right? It's also something you talk about in math. So important that you know something measurable, you can measure it, and it can change. Pause to write that. Next, we're going to do potential energy. Potential energy is stored energy. Potential energy depends on gravity. The higher the object, the more GPE it will have. Right? Obviously, right here, we're talking about GPE because we're talking about the height, right? Not chemical energy, not elastic energy. This is GPE. Then we have kinetic energy. Kinetic energy is the energy of motion. Kinetic energy depends on an object's mass or speed. A large ball rolling has a more KE than a small one, right? If something has bigger mass, it is heavier, it's going to have more kinetic energy. Right? And then finally, the sum of all mechanical energy is your potential energy plus your kinetic energy. Right? If you need to pause and make sure everyone has it, here is a good zoomed in picture of the foldable. Right, now we're going to go ahead and fold it and get it onto our paper. Right? Make sure you're following the instructions very carefully and you are listening. Alright, this is kind of what our foldable is going to look like when you're finished. Let me show you how we got there, right? So, unfolding the whole thing, right? So, we are on the inside, right? The first fold that we're going to need to make is this bottom right, or bottom left corner, excuse me, right? This corner is going to come to about right here, right? So, you're going to take your corner and fold it up like that. You can see how the edge of the paper lined up right here with this corner, right? So it's right here, and we're going to make a big crease, right? So now what you should be able to see is the pendulum on the inside, and you should be able to see that little like blast down here. So again, that was your bottom left corner, comes to about right here. It's kind of where these lines line up right here. So right here to that right there, make a big crease. Right, and now from here, you're going to take this top corner up here, right, and fold it down to kind of meet right here where these two triangles are. It's over here on the side. So it's this top corner, right, it's where that fold is in the paper, right. You're going to take this down, right, and it folds just like that, right. Basically, what you need to see is the title right here, the little blast. You should be able to see this corner, and you should be able to see this part of the pendulum right here, right? So again, from the start, bottom corner to about right here, fold it up. This top little fold right here goes to about here-ish in the paper, right? Wow, that was perfect, right where my finger was, right? And it should look like this, right? If you need to re-watch that, we can. This paper is going to go on the back of our foldable from earlier this week. So take this paper out of your binder, flip it over to the back. We're going to put some glue on the back of this and get it onto this notebook paper. Make sure that you are borrowing glue from someone if you do not have one, right? And take care of my glue that's left out on the tables. Glued it on here, just like that. This paper should go into your binder. You should have front and back foldables on your paper. and put it on in. Alright guys, the next thing we're going to be doing is the comparing potential and kinetic energy paper that looks like this, that has the roller coasters on it. Go ahead and pause the video and pass out this paper so everyone has it in front of them. Alright, what we're going to do with this paper is we're going to go section by section. Right, so there is like 4 pages to this. Right, so we're going to go for the first part together, right, the first page, right, and I'm going to go through and explain how you're going to be doing this, and then you are going to get the chance to do the next pages. I'm going to explain it and then give you some time to work and then come back and give you the correct answers, right? So let me scroll down. Right, so first of all, at the top, right, you should be writing this with me, right? What is potential energy, right? You could write a lot of things for that, but what I want you to write is stored energy, right? That is what potential energy is, right? And then it asks what is kinetic energy, right? And we know that that definition is energy of motion, right? So those should be 2 really easy questions to answer. So make sure you have that. Right, that'll stay on the screen as I slide down. Right, now we're looking at this roller coaster down here. It says describe the amount using a percentage of potential and kinetic energy at points F and H on the roller coaster. So F at the top and H at the very bottom, right? So a percentage is always going to be out of 100, right? So if we're looking at F, right, that's the tallest off of the ground it's going to be. So that would be 100% of our potential energy and 0% of our kinetic energy, right? So when it's at the very, very top, right, it's 100% potential, 0% kinetic. And as it goes down, they flip, right? If you were talking about G, it would be right at 50-50. 50% potential, 50% kinetic, right? As it's at H, that would be 0% potential and 100% kinetic. So let's see how we're actually going to write that, right? So point F, our potential, is 100% and kinetic is 0, just like I said. And then point H, they flip, 0% kinetic, or potential, 100% kinetic. Double check that you have that done. Now we're going to fill in a pie chart below to demonstrate the amount of potential and kinetic energy at point G on the roller coaster diagram. I talked about this a second ago, right? That's right in the middle of these two. So it's going to be about 50-50. So on your pie chart, you're going to just draw it straight down the middle, right? So you have a key that you can make right here, right? One side you're not going to color in. Let's call that our potential energy. The other side, let's color it in and call it our kinetic energy, right? It would be right at 50-50 because it's right in the middle of the top and the bottom, right? And it also asked us to draw a bar graph to represent the amount of potential and kinetic energy at point K on the graph, right? So point K is kind of in between G and H when we're talking about height, right? So it goes back up a little bit, right? So our potential energy, we have gained a little bit. We've gained about 25%, which would be a fourth of this. If we go from this would be half and that would be half, cutting the half in half would make it about a fourth, so 25%. And our kinetic, colored in all the way, would be about 75%, because that's still going really fast, right? So 25%, 75%. Double check that you have that done. You can pause the video here if you need to. Right, now what we're going to do is you're going to move on to this next part, right? Doing 5, 6, there's another 6, 7, 8, 9, and 10, right? I'm going to give you about 5 to 8 minutes to work on just this part, right? We're talking about from question 5 down to question 10. You're not flipping the paper over, just this page right here. 5 to 10 minutes on the timer, or 5 to 8 minutes, sorry, on the timer, and after that time is up, we will come back and review the answers. So go ahead and pause and set a timer. All right, now we are ready to go over it. So sliding down, right? Now we're talking about a pendulum here, right? And I don't want you to worry about copying the answers down yet. I want you to look at this pendulum with me, right? So this is kind of like a ball on a rope, right? So they pull it back and then drop it, right? And it's going to swing back and forth, right? So our highest points are A and E. So there's going to be the most potential energy. And then when it's at C, that's the lowest point that it can go because the string's holding it up, right? So describe the amount using a percentage of potential energy at C, right? Well, that's at the lowest point it could possibly go. So, of course, our percentage is going to be 0, okay? Fix that if you need to. Then we have question 6. Describe what happens from the amount of kinetic energy from point B to D, right? So, going from here to here, right? Just kind of in the middle, right? I put it increases from B to C, and then it decreases from C to D. So we're talking about kinetic, right? It speeds up, and then it slows down as it goes up. And then it speeds up, and it slows down. Right? Check that you have that. Number 6, set a pie chart to describe the amount of potential and kinetic energy at point D. Look at our pie chart. It looks just like it did on the roller coaster because this is the lowest, this is the highest. So D is right in the middle. It splits it half potential and half kinetic, right? Don't forget that you did your key. Right, number 7, right, our bar graph to represent the amount of potential and kinetic at B, right? Again, this is the top, this is the bottom, so B is right in the middle. So it's going to be 50-50 again, 50% potential, 50% kinetic. Don't forget to put PE and KE down here. That's going to be confusing if you don't do that. So pause if you need to. Let's get that down. Question 8, 9, and 10. It says, describe what happens to the amount of kinetic energy from point E to C. Right, so let me slide back up. Right, from E going down to C. Right, as you drop it, it goes faster and faster and faster till it gets to C, and then it slows down as it goes back up. So from E down to C, the kinetic energy is going to increase. Number 9, describe what happens to the kinetic energy as the rock rolls from point Y to Z. Now we're looking down here, right? Kinetic energy. As it goes from Y to Z, it's from the middle, it's going down, 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 goes faster, faster, faster. The kinetic energy increases. Draw a bar graph to represent the amount of potential and kinetic energy at point Y. This is kind of like a roller coaster, right? Y is right in the middle. X is at the top, Z is at the bottom. This would be 100% potential because it has the potential to go down. This would be 100% kinetic because it's going really, really fast. Right here in the middle is going to be 50-50. So just like our last one, 50% potential, 50% kinetic. Don't forget your labels. Pause to get that. All right, now we're scrolling down. We're looking at, sorry, I forgot to tell you. Now you're going to answer questions 11, 12, 13, and 14. This one's a little bit less questions to answer, so let's try to go with 5 minutes to answer all these questions. If we need a little bit more time, that's okay, but let's go for 5 minutes. So go ahead and answer and go. All right, now I'm going to scroll over and let's go over it. Right, on question 11, it's talking about the people jumping on the trampoline. It says, which image shows the jumper with the greatest potential energy, and explain your answer. Right, image A, the position of the jumper is at its highest point compared to jumper B. Right, so it's talking about gravitational potential right here. Right, so this one is higher off the ground than B, so it has higher potential energy. right? It says fill in the pie chart to demonstrate the amount of potential energy and kinetic energy for diagram B, right? We're filling in the whole thing as kinetic because they're moving the fastest when they're at point B, and it stops them so that they can go back up, right? So that would have to be at the fastest point for the pie chart. Question 13 and 14. Right, this is a new diagram. The diagram shows a soccer ball being kicked. Create a line graph showing what happens to the amount of kinetic energy from points A to D. Right, so A is when it's on the bottom, right? They kick it, it goes faster and faster. It actually slows down. Sorry, that would be the fastest it would be. They kick it and it slows down as it goes higher and higher and higher, right? Because gravity's pulling on it as it goes up. Right, so this is what your line graph should have looked like. At point A, that's going to be the fastest it's going when they kick it. And then as the ball goes up into the air and gravity pulls on it, it's going to go slower and slower and slower. So that's what it should have looked like. Make sure you labeled it. You had a title for it, soccer ball energy and kinetic energy down here with the points. Right, it also says describe what happens to the potential energy of the soccer ball at each point listed below. Right, so looking at these points, right, at A, as the soccer ball just sits on the ground, it has no potential energy. It's sitting on the ground, there's nothing pulling on it. I mean, gravity's pulling on it, but it can't go any further down. Right, B, the potential energy increases to about, that's what that symbol means, is about 25%. C, it increases to about 50, and D, it increases to about 75. So make sure that you have that as done as well. All right, next page. Right here you have question 15, 16, 17, 18, and 19. Right, we're going to finish off this paper. Let's go with about 5 more minutes. If you need up to about 8, that is totally fine. Right, so go ahead and pause and get some time to work. Right, now it is time for us to go over it, so let me slide down. Right, number 15, on the roller coaster diagram, label the point on the track with the lowest amount of potential energy with the letter A. Label the point on the track with the lowest amount of kinetic energy with B. Right, the lowest kinetic is, of course, is going to be at the top because it stops. And the lowest potential is going to be at A because it's at the closest to the bottom. Right, 16. Draw a bar graph to represent the amount of potential and kinetic energy at point Z. Right, looking at point Z, it is at the highest point. So the potential is going to be the highest because we're talking about gravitational potential. Right, at the very top, it's going to be the highest. So 100% potential. And just like the roller coaster, it's stopped. It's about to go down. Same thing in Z, right? It flies up, it stops for a second, and then it's starting to fall back down. So our kinetic is going to be 0. And I just drew a little line there to represent the 0%. Right, let's look at the last 3 questions. Right, number 17. Fill in the pie chart to demonstrate the amount of potential and kinetic energy at point X. So looking at our skateboard right here, right, it is about in the middle, right? At the bottom would be down here. The top is up where Z is. So X and Y are both about in the middle. So I said 50-50, right? 50 potential, 50 kinetic, straight down the middle in half. 18 asks for a bar graph of the kinetic energy at points X and Y, right? So this is not potential and kinetic like this. This is just kinetic energy at X and Y. If I look at my diagram, they're about at the same place. So our kinetic energy should be about the same, right? If it were up here, obviously our kinetic would be lower. And if it was at the bottom, it'd be higher because it'd be going faster. But these two are the same. So X and Y, I said they were both about 50% of our kinetic energy. And don't forget all of our labels. Pause there to make sure we have that done. And the last question says, describe what happens from the amount of kinetic energy from point X to Y. And I said the kinetic energy increases to the bottom of the ramp, then decreases to point Y. So right here, right, the kinetic energy increases from X to the bottom and then decreases going to Y. Right? That's what I was just talking about a second ago, right? All right, so this whole paper should be done. Right, this paper is going to go into the box today. Make sure one person takes this for your table and puts it up. You should be about at the end of class. If you are not, you have the extra work coloring paper that you may work on. And guys, I hope you have a great rest of your day. I will see you in class tomorrow.